Question 8 for 2024 has area and volume. We're dealing with a cylinder with height 15 and radius 5, and we're given the net of the cylinder. We're asked to write the dimensions of the rectangle. So when we have the height is 15, so we'll do that as the height, and then the length is 2 pi r. When the circle is opened up, it's still got 2 pi r of length, so 2 by pi by a radius of 5 is 10 pi, which is 31.42 to 2 decimals, but we just want 1, so 31.4 by 15. Then we have a different cylinder with height of 22, so we have a radius of a sphere, and we're told to use Pythagoras. So what's my measurements that I have here? So I have half the height, so that's going to be 11, and the diameter of my cylinder is 12, so the radius of the cylinder is this one. This is going to be 6. That helps me get the radius of the sphere, or is equal to the square root of 6 squared plus 11 squared, which is 36, and 121, which is 157. We're asked to find the volume of the sphere here in bold. So the volume of a sphere, 4/3 pi r cubed, 4/3. We'll use pi on the calculator, by the square root of 157 cubed. Just be careful the way you type it in. This is giving me 8240.2, 8240 to 1 decimal place, so 0.2 cm cubed for part B. Part C, we have an ornament made up of 2 cones shown here, and they have the same base, which we can see. The bottom cone's inverted, which we can see. We have a vertical cross section taken here, and we have triangles ABC and ABD. We can see that here in the triangle. ABC is this one, and then the one below, ABD, is this one. We can see ABC is the top one, all the points are on the circle, and AD and CD intersect at E. So we have right angles in here. The diagram is symmetrical about DC. Why is the angle, or the size of the angle, CBD 90? CBD is this one. And this is an angle standing on the same arc. That's theorem 19 from junior cert. Here we have a diameter of a circle. So this angle is 180. So therefore this angle is 90. So here we're going to state that. Maybe angle at center twice angle standing on same arc. That's probably enough information here. Therefore 180 divided by 2 is equal to 90. So the size of the angle CBD is equal to 90 degrees. Then we're asked to hence or prove that the triangles BCE and DBE, BCE is this one here. We're asked to prove that this one is similar to the DBE, so the one down the bottom here. So similar triangles, same angles, so they both have a right angle. We can see here, right angle and right angle. It might be easy to just number them, 1, 2, 3, 4. We've already shown that the size of angle 2 plus the size of angle 3 is 90. And we also know, because we have a right angle in the triangle, angle 1, the size of angle 1 plus the size of angle 2 is 90. And therefore, we can say that angle 1 is equal to angle 3. The size of angle 1 is equal to the size of angle 3. Similarly, we can say that angle 4 plus angle 3 is equal to 90. So therefore, angle 4 2 plus 3 is 90. Angle 4, the size of it is equal to the size of angle 2. Therefore, similar triangles. You could expand on this a little bit, but that's the maths behind it. Part 3, the top cone has a radius of r and a height of h, that is EB is equal to r. So we'll draw this triangle out again. This was the top one we were using. This was CEB. We have a right angle. We had the angle 1 and the angle 2. And in the bottom triangle, we had the angle 3 and 4, but we're going to rename them 1 and 2 for similar triangles. So if we look up, angle 3 we know is equal to angle 1 from above. So I'm going to put angle 1 here, and angle 2 will be here, and this is EDB. So what are we told? We're told EB is equal to R, and EC is equal to H, and we're asked to show that this R squared is equal to 20H plus minus H squared. So EB is a common side, so this is R. So we need to get this one here, ED, and if we look at the diagram, we're told that this guy is 20 from here to here, so this guy is going to be 20 minus EC, which we were told was H. So this is 20 minus H. So setting up our fraction for similar triangles between 1 and the right angle, we have H. So over the same side in the other triangle, 1 to the right angle will be R. That's equal to R in this case, over right angle to number 2 is 20 minus H. So we're going to get R squared is equal to 20H minus H squared for part 3. And in part 4 we're asked to write the volume of the cone in terms of H and pi, and hence find the value of H that gives max. So we need differentiation here. So let's start with the volume of the cone. The volume of a cone is 1/3 pi r squared H. And we have some information in terms of R and H here. So we have R squared from above, so let's change R squared in terms of H. So we're going to get 1/3 pi by R squared, which is 20H minus H squared. That's times H. So we're going to get pi over 3 times 20H squared minus H cubed. So I might just multiply this out. Actually, that's going to be 20 over 3 pi H squared minus pi over 3H cubed. This is the volume of my cone. So the value of H that maximizes it, we want to differentiate the volume with respect to H. So that's going to give the 2 by the 20 over 3. So that's going to be 40 over 3 pi H minus 3 pi H squared over 2. This will be equal to 0 for the max value, so they'll be equal to each other. 40 pi H over 3 will be equal to 3 pi H squared over 3, multiplying by 3, dividing by pi, and dividing by H. We'll be left with H is equal to 40 over 3. And I think that's in centimeters.